you. In the meanwhile, let's wrap up our discussion of sums, okay, by sort of summarizing what we know so far. So I'll tell you, we've computed two sums. We've computed T4 of n, which is the running time of algorithm 4, is equal to 5 plus 10n. Okay. Now, with some effort, we computed T2 of n, which is equal to 2 plus 6n plus 3n squared. Okay. And you may wonder, what about T3 of n and T1 of n? Okay, equals what? Okay, well, you can go ahead and compute T1 of n. Now you have the tools. I'm not going to spend the time here. Okay, this is a nesting of sums where there are three sums. So you start from the innermost, then move out, so you have to move out twice. Okay, and if you went and computed it, you will find that T1 of n is equal to 2 plus 31 over 6n plus 7 over 2n squared plus 1 over 3n cubed. Wow! Okay, so complicated. Okay, and then T3 of n is a recursive, algorithm, and its running time is given by a recurrence or a recursive function. And to solve that recursive function is very hard. And if you want to go and try to solve that recursive function and figure out a formula for T3 of n, good luck. I don't envy you. Okay, but it turns out that we can bound the running time at least. We can bound the running time, and we can say that the running time is at most, 12n log base 2 of n plus 3 minus 9. So the running time is at most this complicated formula. Okay, now, let's say we plot these formulas on a graph. Okay, let's plot these formulas on a graph. Okay, so we've gone through some painstaking effort. Okay, and we've gotten formulas for the running times, and they're very complicated looking formulas. Okay, and now typically in practice, you have the input size n, and we're interested in how the running time scales with n. So typically we might divide the running time by n. Okay, so let's divide this guy by n. Okay, in which case we have 5 over n plus 10. Okay, so that's the running time that's divided by n. Okay, and you can see that this running time is, starts at 15 when n is 1 and then gradually drops to 10. So if this is n, okay, and this is the running time, the running time of n divided by n, and if this is 10, okay, then this guy's running time, T1, looks something like that. So T1 of n. Okay, nice. Okay, and if we plot T3 of n, if we divide T3 of n by n, so divide by n, this n disappears. That's, divided by n, it's small, so you have basically log 2 of n, 12 times log 2 of n plus some constants. If you plot T3 of n, it's going to look something like this. It's going to start here. Oh, I don't have a working red, so let's try working blue. Okay, so this is something like T3 of n. Okay. If you divide T2 by n, the n comes over here, you get 2 of n plus 6 plus 3n. So that's going to be, growing something like linearly with n. It's going to start out more than linear but approach linear. Okay. And, finally, if I divide T1 by n and plot, I'm going to get, 2 over n plus 31 over 6 plus 7 halves n plus 1/3 n squared. So it's going to look, something like that. Okay, so this is T1 of n. Okay, and this is T2 of n. Okay, and, we've got these nice complicated formulas. Okay, and first of all, we're interested in, which algorithm to pick. And second of all, we're interested in what is the running time of that algorithm. What is the running time that captures the essence of the algorithm. Okay, and so which algorithm to pick is a messy business. Okay, so which algorithm to pick? It's a messy business. Okay. And why is it a messy business? It's a messy business because you see that, sometimes one algorithm is better than another. Okay, like these algorithms are all better than T1, and then all of a sudden they get worse. Okay, so, which would you pick? It depends on n. Okay, but here's the fundamental insight. When it comes to computer science, we're not interested in using computers to solve problems with inputs of size 3 and 4 and 5. No, those are of no use to us. We are interested in solving problems with inputs of size 1 million, 2 million, 10 million, 1 billion, 1 trillion. Okay, and so that sort of makes life a lot easier for us. It makes life a lot easier. Makes life much easier because we only care about large n going to infinity, what we say asymptotic in n, because we care about large asymptotic n goes to infinity. Okay? And once we realize that, okay, we immediately notice that in this regime, it's clear that this algorithm is the best when n becomes large. Okay, this guy's coming down to 10. Okay, so the running time is basically approaching 10n, and all those guys are going off to infinity. Okay, so algorithm T4 of n is best in this asymptotic regime, and more importantly, when we enter this asymptotic regime, we might think, well, okay, so what is the running time? We actually say that the running time of algorithm 4. So this, sorry, by the way, is algorithm 4. The running time of algorithm 4, we say that it is linear, okay? Because when you divide it by n, it's approximately a constant. Or T4 of n is equal to 5 plus 10n. Okay, and we say that this is growing linearly with n. So we say that T4 of n is linear. Okay. And we mean something very special by that. And what we mean by that is, the essence of the algorithm is linear. Okay. And I'm highlighting the word essence of the algorithm. The essence of the algorithm is linear. And what we mean by that is, okay, so someone programmed it, and they got a running time of 5 plus 10n. And so, that's because, remember, there was this loop, single loop, and you did a work of 10 in that single loop. Okay, someone else came and said, you know what? I can, reconfigure my hardware, and you are mostly using, multiplications. So I'm going to increase the speed of a multiplication, from by a factor of 2. So this 10 becomes 5. So now the runtime becomes 5 plus 5n. Oh, big deal. I don't want to focus on these hardware optimizations. And then someone else comes along and says, you know what? You're using 10 multiplications in your loop. I can do it with 8. So these minutiae, these small optimizations might make the running time, maybe the startup cost can be reduced to 3, and then maybe you can, reduce multiplications from 10 to 8. So you might be able to get 8n. So your genius friend managed to get it down to 8n. Okay, and you look at this and say, oh, wow, this minutiae, we care about this? No, that doesn't capture the essence of the algorithm. See, there's something fundamentally different between this algorithm, which is having a running time that, involving n, and this algorithm, which is having a running time that is involving n cubed. Okay. And so what we say is that, we're going to ignore constants, additive and multiplicative constants, we're going to ignore. So roughly speaking, we say that, this running time of T4 is basically linear. T4 of n is basically linear. Okay? And correspondingly, T1 of n is basically, if you ignore constants and additive constants, then, it's basically, n plus n squared plus n cubed. Okay? And we'll soon see that we can even ignore these small guys because the essence of the algorithm is captured by the n cubed term. So we say this guy is n cubed. Can we say that this guy is n squared? Can we say that this guy is n times log n? Can we say that this guy, so if I forget about dividing by n, we get n here. This guy we say is, linear. Okay. So let's define this sort of way of talking about running times that captures the essence of an algorithm and only cares about n being large. Okay, so let's most of the time in computer science we're interested in algorithms which are linear, So let me define for you the set of functions that are linear in n. Think of n as the size of the input. So we're interested in running time as a function of the size of the input, and the most beautiful, the best algorithms that we like to create are the ones that are linear in n. Okay? And notice I said I'm going to define a set of functions that are linear in n. And the first thing you must think to yourself is, well, but linear in n, isn't that one function? There's one function that's linear in n. So I want to define a set of functions. Okay? So, this falls, under our discussion of asymptotic analysis, or how to compare runtime functions t of n, when all you care about is n goes to infinity, and you don't care about these minutiae of multiplicative or additive constants. Don't care about additive and multiplicative constants. Okay. Now, in computer science, some people call this, O analysis, or big O analysis, or order analysis. Order analysis. But the formal mathematical term is asymptotic analysis. So let me define the set of functions that are linear. Okay, so a function belongs to this set. So this set of functions that are linear we call theta or big theta of n. N for linear because n to the power 1. The big theta means, equal to. Think of big theta as equal to. Okay, so the set of functions that equals the linear functions. Okay, so we say that the function t of n, or usually we just say the function t belongs to the set big theta of n. So that belongs to the set of linear functions if, now here's the formal definition, if there are constants little c and big C such that little c times n is less equal to t of n, which is less equal to big C times n. Now sometimes we will say that these inequalities only have to hold for n large enough. Okay, so we would say for n bigger than or equal to some n0. Okay, but you don't lose much generality in this formulation, especially if we assume that t of n is always a positive function, so t of 1 is positive. You don't have negative or zero runtime, so t of 1 and t of n is a monotonically increasing function. Okay, so runtimes typically increase as you increase the size of the input space. Now we can develop a much more general asymptotic analysis, but for most practical purposes in computer science, we can assume that t of n is positive and increasing. Okay, sometimes okay, now this is the formal mathematical definition. Okay, and you'll have to sit down and parse it. Let me tell you what's the more practical definition. The more practical definition is you just compare t of n to n. So compare t of n to n. What that means is you divide t of n by n. Okay, so we're comparing t of n to divide it. Okay, and one of three things happens because this is positive and increasing. This is a positive function. So one of three things happens. Okay, either this thing, when you divide by n, goes off to infinity. Okay. Or it goes off to 0. Okay. Or it goes to a constant that's bigger than 0. One of three things happens. So when you take this limit, so this is what we're talking about here, is in the limit as n goes to infinity. And I know there's the mathematical among you who are saying, well, how do we know the limit exists? So when the limit exists, we can certainly do this. Sometimes the limit might not exist, so we talk about lim sup and all that stuff. Forget about all those details. In practice, these functions are monotonic and increasing, and this limit either goes to 0, infinity, or a constant that's bigger than 0. Sometimes the limit may not exist, then we need to, resort to the more formal technical definition. Okay, so this is the set of functions that are linear in n. Okay, so the functions that are linear in n are the ones for which the limit goes to a constant. So we say that this is theta of n. So any runtime function for which this limit goes to a constant that's not zero, that's belonging to the set theta of n. Okay. Now it's interesting. We do have names for these sets. This is, these functions are strictly bigger than n because the ratio is going off to infinity. We call this set of functions little omega of n. And we call this set of functions the ones that, when you divide by n go to zero. So they're much better than n. They're strictly better than n. They're less than n. We call this little o of n. Okay, but that's not a big deal. Don't worry. Okay. And things get complicated, because we like to have notation for everything. And now we're just having excess and excess of notation. Okay. Okay. If the ratio is either a constant bigger than zero or going to infinity, we say that, this is the set big omega of n. Okay. And if it's a constant bigger than zero or going to zero, we say that this is the set big O of n. Okay. So now I want to emphasize that these are just notations that define different kinds of sets. The most important is the theta of n, which is the set of functions which are linear. Okay. So now let me give you, so think of this as the functions which equal linear. So theta of n, okay, is the functions t which equal, I'll put it in quotes, linear. Okay, omega of n are the functions t of which are in some sense strictly greater than linear. Okay, and the set of functions little o of n are the functions t which are, the quotes go here, which are less than linear. So, linear can be used to define three sets of functions. The functions which are equal to linear, where the limit is a constant. The functions which are strictly greater than linear, which we call little omega of n. And the functions which are strictly smaller than linear, which we call, little o of n. And, what is big O of n? Big O is these two sets combined. You're either less than linear or linear. So you can think of big O as less than or equal to linear. And you can think of big omega, so big O, big O of n is t is less than or equal to linear. And big omega of n is that t is greater than or equal to linear. Okay, so this is all notation, but let's focus on the set of linear functions. And let's do some examples. Okay, so here are examples of linear. Okay, and let's do some examples of not in the set theta of n, not linear. Examples of not linear. Okay, so examples of linear. 2n plus 7. That's the classic linear function. And when we were in high school, we said, oh yeah, that's a linear function. It's got a slope and an intercept. Nice, blah, blah, blah. Okay, linear, classic linear. Okay, but now here's an interesting one. 2n plus 15 square root of n. Okay, so I say that that's an example of linear, and you look at that and you say, wow, I've never seen anything more nonlinear than the square root of n. So how can you call that linear? And that's where we have to come back to this definition or this ratio, sort of asymptotic, this limiting ratio. So let's look at the ratio of 2n plus 15 square root of n divided by n. It's the limit as n goes to it. Well, this is equal to 2n over n, which is 2, plus, okay, the limit, plus 15 over square root of n, because square root of n over n is 15 over square root of n. 15 square root of n over n is 15 over square root of n. And as n goes to infinity, this term goes to 0, so this goes to the limit 2, which is a constant bigger than 0. Okay, so according to this definition, it fits into the set of functions we consider linear. And what's the essential idea here? The essential idea here is that, 2n plus 15 root n, the root n term is negligible compared to the 2n term when n gets huge. Okay, so we can just ignore it, and then you have the linear part. Okay, so that's why we say it's linear. Another way of viewing it formally from the definition is, look, 2n plus 15 root n, 2n plus 15 root n is certainly greater than 2n. Okay, so that's clearly linear. Okay, and it's certainly less than, 17n, because, root n is less than n, so this is less than 70. So I can bound it from below and from above by a linear function. That's the technical mathematical definition of linear, okay, of the set of linear functions. You can bound from below and above by linear. But you can see that if you can bound from below and above by linear, then when you divide by n and take the limit will go to a constant. Okay, so even though this is a nonlinear function, it belongs to the set of asymptotically linear functions. Okay, let's do more examples. 10 to the 9n plus 3. Okay, so when you divide by n, you get 10 to the 9 plus 3 over n, take the limit. This is a classic linear function. And we say that this is linear. But now you look at me and say, whoa, aren't we supposed to use this to compare the running times of functions? And so what you're saying is that this guy is linear and that guy is linear. But wait a minute, this is 2n and this is 10 to the 9n. And then remember we said we're not going to consider, we're going to ignore minutiae like multiplicative and additive constants. So effectively we're ignoring 10 to the 9 compared to 2. Oh, that's a horrible thing to do. And yes, in practice we do care about this 10 to the 9. But in order to capture the essence of the algorithm, they are both linear algorithms. Okay, and what linear has the property of is that if you double the input size, you double the running time. And that essence of the algorithm is holding whether you're talking about this guy or that guy. Okay. So linear captures the essence of the algorithm, not necessarily the actual runtime. Okay. And this method of capturing the essence of the algorithm has withstood the test of time. In other words, if you have an algorithm that has a running time of, let's say, 10 to the 7n, and you compare that with someone else's algorithm, which has a running time of, 50 n cubed. Okay. Well, when we capture the essence of the algorithm, we say this is linear, and we say that's cubic, and we prefer this, even though on an input of 1, this guy has a running time of 50, and this guy has a running time of 10 to the 7. But we don't care we don't care about 1, n equals 1. We care about n equals, let's say, 10,000, and at n equals 10,000, let's see which one is better. You'll find this is better. And that's just at 10,000. And so this capturing the essence of the algorithm using this notion of ignoring additive and multiplicative constants and looking at the set of linear functions, that has withstood the test of time. Okay, let's do another example of linear. Okay, 2 to the log base 2 of n plus 4. And you look at that and say, whoa, that's exponential. Okay, now this is where you need to use your knowledge of logarithms. 2 to the log base 2 of n plus 4, 2 to the log base 2 of n plus 4. So when you have a sum in the exponent, it translates to multiplying. So this is 2 to the log base 2 of n times 2 to the 4. 2 to the 4 is just 16. So this is 16 times 2 to the log base 2 of n, but 2 to the log base 2 of n, that's by definition of log base 2. This guy is exactly n, so this is 16n. So this is just, I'm tricking you. This is just a fancy way of writing 16n. That's clearly linear. Okay. Now, examples of not linear. Okay, 10 to the minus 9n squared. Wow! 10 to the minus 9n squared. So minute running time as long as n squared is less than 10 to the 9. But once n squared gets big, it's going off quadratically, so non-linear. Okay. 10 to the 9 square root of n plus 15, not linear. Okay. So now, let's see which of these sets do each of these functions fall into. So this is, when you divide by n and take to infinity, you'll find n squared over n goes to infinity. So this guy belongs to omega of n. It's in the set of functions that are strictly greater than linear. This guy, when you divide by n, so this becomes 1 over root n, this becomes 15 over n, and so when you divide by n and take to n going to infinity, this goes to 0. Okay? And so this belongs to, So this guy belongs to little o of n. Okay, it's strictly smaller than linear. Okay, let's do a couple more examples. N to the 1.0001, not linear. The exponent is slightly larger than 1, but that's enough to make it not linear. When you divide by n, so when you divide by n, you have n to the 1.0001 divided by n gives you n to the 0.0001. Take n to infinity, that goes to infinity slowly, but it gets there. Okay, so this guy is in little omega of n. What about n to the 0.99999? Looks like almost linear. Not quite. When you divide by n and take to the limit to infinity, it goes to 0. So this guy is in little o. This guy is in little o of n. You see that any function either belongs in this set, or this set. It's either equal to linear, strictly greater than linear, or strictly less than linear. Very nice. Okay. What about n over log n? That's an interesting one. N over log n, okay, that's not linear. Okay. But it looks close to linear. And in fact, when you divide by n and take the limit, it goes to 0 because you get 1 over log n and log n goes to infinity. So 1 over log n goes to 0. So this guy, even though it looks close to linear, and it's in practice, it's not easy to distinguish n over log n from 50n. From n over 50. Okay? It's in practice hard to distinguish because to distinguish n over log n from n over 50, n has to be bigger than 2 to the 50. So it's hard to distinguish in practice, but from the perspective of capturing the essence of the algorithm, this is not a linear algorithm. It's strictly better. It's strictly faster. So this is strictly smaller than linear. So this is little o of n. And of course, the obvious case, 2 to the n, well, that we call an exponential algorithm. Okay. And so this is in little omega of n. Okay. So, practice. Let's do some practice. Okay. Before we get to the practice, let me mention, by the way, so this is the definition of the set of functions that are linear. We can define the set of functions that are quadratic. So if I want to define the set of functions that are quadratic, I would say define that as theta of n squared, and we say that t is in theta of n squared, and it's the same definition where you have replace n with n squared. So it's bounded below and above by some linear multiple times n squared, and you compare, if you want the pragmatic definition, you compare n to n, you compare t of n to n squared, and so you have t of n divided by n squared, and the same rules apply. We say that if t of n of n squared is going to infinity, we say that the algorithm is strictly, worse, or the running time is strictly larger than quadratic, and we call that little omega of n squared, or it is quadratic, theta of n squared, or it's much better than quadratic, it's strictly smaller than quadratic, little o of n squared. And you will soon realize that I can put any function you want here. Okay. And we can talk about the set of functions that are asymptotically equivalent. So we say the set of functions that are asymptotic equal to f. So the set of functions that are asymptotically equal to f, we say that t is in the set theta, big theta of f, if there are constants c and c such that c times f is a lower bound for t of n. Oh, there's no n squared here. This is still t of n, okay, which is less than or equal to big C times f. So the set of functions that are asymptotically equal to f. And if you want the pragmatic approach to deciding whether you're asymptotically equivalent to f, you compare t of n to f of n. Okay? And so instead of dividing by n or n squared, you divide by f of n. And if it goes to infinity, you're in the set that's strictly faster, increasing faster, strictly faster than f, or you're in the set of functions that are asymptotically equal to f, so we say theta, big theta of f, or you're in the set of functions that are strictly smaller than f. Okay? So this is just a discussion about linear or quadratic, or can be generalized to any f. So let me give you some examples. Okay, log. We say that the running time, if t of n is log n, we say that the running time is logarithmic. Okay, if t of n is n, that's linear. If you have n log n, we say that that's log linear. If you have n squared, we say that that's quadratic. If you have n cubed, cubic algorithm. If you have 2 to the n, we say that your algorithm's running time is exponential. Okay, and if your running time is n factorial, this is what we call a factorial algorithm. And if your running time is n to the n, okay, so this is an order of increasing running times, asymptotically increasing running times. If your running time is n to the n, we just say that's bad. It's bad. So this is factorial. This is exponential. This is cubic. This is quadratic. This is log times linear. This is linear. And this is log. We would love to have algorithms that are logarithmic in running time. And one such algorithm is binary search. Most algorithms that we are proud of are linear. N log n algorithms like sorting, they're okay. N squared, we can deal with. N cubed, we're running into trouble. Exponential, we're dead. We cannot deal with exponential algorithms. Factorial algorithms, we're dead. And n to the n, okay, we need to get another job. All right. So let's do some practice. Practice. Okay, so 1. What you will observe that when you take this limit and take the limit to infinity, the correct function to put in here and get a constant in the limit, if you have a polynomial, is a polynomial with the same highest order as in t. So for polynomials, the asymptotic behavior, sometimes we call that the growth rate. Okay, so that's the asymptotic behavior. Is the highest order of the polynomial. So examples. Okay, 2n squared. This is in the set theta of n squared. Okay, n cubed plus n root n. So this is a polynomial. The order here is 3/2. The order here is 3. So this is in theta of n cubed. Okay. Now, one that you have to be careful with is something like n log n. This is not in the set theta of n, even though the highest order of n is n. The highest order of n is 1. But there's this additional log n term that's multiplying. So when we talk about the highest order, it means that the highest order that's multiplied by a constant. So here the order is 1, but it's not multiplied by a constant. Okay. So quick question. What about n squared plus log to the 300n? Okay. It turns out that any polynomial smashes a logarithm. So this is in theta of n squared. Okay. What about sums? Can we get quick asymptotic analysis of sums? It turns out that there's a very easy rule of thumb that most of the time works. So it's not a theorem or anything. Okay, so rule of thumb for nested sums. So this is a rule of thumb. Okay, so if you have a nested sum, like the sum from I equals 1 to n, the sum from j equals 1 to n of I times j. Okay, or the sum from I equals 1 to n, the sum from j equals 1 to I of I times j. If you remember, we actually computed this sum. Okay, now the rule of thumb says, look at the order of the summand. So we say that this summand has order 2, because there's a product. So you can think of the I and j as playing similar roles. So the order of this summand is 2, and then count the number of nestings. So there are 2 nestings. Add those together, you get 4. And so this sum is in theta of n to the 4th. Same thing here, 2 nestings, order of 2. So this sum is in theta of n to the 4th. Now you can go and compare with the actual exact sum that we got and verify that it is indeed in the set of functions that are, that the set of functions theta of n to the 4th. So the highest order in the polynomial will be n to the 4th. Okay? So we have sort of answered all the questions that were plaguing us. we can compute sums. But when it comes to comparing runtimes, we don't need the exact value of the sum. We just need the right order, okay, in order to extract the essence of the algorithm. Okay. And so we define this set of functions, for example, the set of functions that have the same order as linear. We call that theta of n. The set of functions that have the same order as quadratic, theta of n squared, and so on. So we can quickly, if we can quickly estimate the running time from a sum in terms of what's the order, okay, and that basically corresponds to what's the highest order of the polynomial that describes the running time, then we have a quick estimate of the essence of the algorithm. Okay. And so, this order analysis, removes a lot of headaches when it comes to comparing whether one algorithm is better than another. Okay. So, with that in mind, okay, we realize that we only need to, in some sense, accurately approximate sums. And so now what I'm going to give you is a gem. Okay? And this gem is using calculus, i.e. integration, to quickly estimate sums. Okay, so let's first erase, and then I'll show you the integration method.